In the summer of 1915, while serving on the Russian front during the First World War, a German physicist named Karl Schwarzschild did something extraordinary. Huddled in a trench, surrounded by the chaos of artillery fire and the dying screams of soldiers, he solved Albert Einstein's field equations. Einstein had only published his general theory of relativity weeks earlier, describing gravity not as a force, but as the curvature of space-time itself. Schwarzschild took those equations and found an exact solution, one that described the geometry of space-time around a perfectly spherical mass. What he discovered would haunt physicists for decades. His solution predicted something so bizarre, so fundamentally at odds with our intuition about reality, that even Einstein himself refused to believe it could exist in nature. Schwarzschild had discovered black holes. Within months, Schwarzschild would be dead, not from enemy fire, but from a rare autoimmune disease contracted in the trenches. But his equations lived on, hiding within them a prediction so strange that it would take half a century before anyone took it seriously. His mathematics described an object with gravity so intense that nothing, not even light itself, could escape once it ventured too close. A region of space-time so warped that all paths lead inward, where time itself stops flowing in any way that makes sense to us, where the very fabric of reality tears apart. Einstein hated the idea. He wrote papers attempting to prove that such objects could never form. They were, he argued, mathematical curiosities with no physical reality. Nature would never permit something so monstrous to exist. He was wrong. Today, we know that black holes are not only real, but common. There are likely tens of millions of them scattered throughout our galaxy alone. At the center of nearly every large galaxy, including our own Milky Way, lurks a supermassive black hole containing millions or even billions of times the mass of our Sun. We have photographed their shadows, detected the gravitational waves from their collisions, and watched stars orbit around them at speeds exceeding 5,000 kilometers per second. But here is what we have never done, and can never do. We have never sent a probe inside one. We have never received a signal from anything that crossed that boundary. We can never, even in principle, retrieve information from beyond that point of no return. Which means that when we ask what happens inside a black hole, we are asking a question that might be fundamentally unanswerable. Not because we lack the technology, not because we need better telescopes or more powerful computers, but because the universe itself seems to have drawn a curtain beyond which no information can pass. And yet we have theories. Brilliant, beautiful, terrifying theories about what lies beyond that veil. Some of them are grounded in rigorous mathematics and decades of careful reasoning. Others venture into territory so speculative that they blur the line between physics and philosophy. All of them agree on one thing, though. If you could somehow survive the journey into a black hole, you would witness the most extreme, most alien environment that exists anywhere in the cosmos. A place where the rules that govern everything else in the universe break down completely. So, let us begin at the beginning. What exactly is a black hole? The answer is simpler than you might think, at least on the surface. A black hole is what you get when you compress enough mass into a small enough space that the escape velocity from its surface exceeds the speed of light. That is it. That is the fundamental definition. Every object in the universe has an escape velocity. For Earth, it is about 11 kilometers per second. Launch something faster than that from the surface, and it will escape Earth's gravity forever. Launch it slower, and it will eventually fall back down. For the Sun, the escape velocity is about 600 kilometers per second. As you compress an object, keeping its mass the same but making it smaller, the escape velocity from its surface increases. Compress the Sun down to about 3 kilometers in radius, and the escape velocity would equal the speed of light. Compress it further, and the escape velocity would exceed light speed. but nothing can move faster than light. So nothing can escape. Not rocket ships, not particles, not even photons of light themselves. This is a black hole. But here is where things get strange. That boundary, the distance from the center where the escape velocity equals light speed, is not a physical surface. You could not touch it. You could not even see it if you were there. It is simply a mathematical point of no return, a border in space-time beyond which all future paths lead inward. We call it the event horizon, and it is perhaps the most important boundary in all of physics. The term event horizon is eerily appropriate. An event is something that happens, and a horizon is a boundary beyond which you cannot see. The event horizon of a black hole is precisely the boundary beyond which events cannot be seen from the outside universe. Anything that happens inside can never be communicated to the outside. The information is trapped forever. Or is it? This question, whether information is truly destroyed inside black holes, is one of the biggest controversies in modern physics. We will return to it, but first, we need to understand exactly what we mean when we talk about the structure of a black hole. The simplest possible black hole, the kind that Schwarzschild first discovered, is perfectly spherical, has no electric charge, and is not rotating. Real black holes are not this simple, but let us start here. This Schwarzschild black hole has two key features. First, the event horizon, located at what we call the Schwarzschild radius. For a black hole with the mass of our Sun, that would be about 3 kilometers from the center. For a black hole 1,000,000 times more massive, it would be 1,000,000 times larger, about 3 million kilometers, or roughly 4 times the radius of the Sun itself. The second feature is the singularity at the center, where all the mass of the black hole is concentrated into a point of infinite density. At least, that is what the mathematics says. Whether there really is a point of infinite density, or whether something else happens that our current theories cannot describe, is one of the central mysteries we are trying to unravel. Between the event horizon and the singularity is the interior of the black hole, a region of space-time that is completely cut off from the rest of the universe. But we are getting ahead of ourselves. Before we venture inside, we need to understand what makes the event horizon so special. And to do that, we need to talk about the bizarre way that gravity affects the flow of time itself. One of the most profound predictions of Einstein's general relativity is that time does not flow at the same rate everywhere. The stronger the gravitational field, the slower time passes. This is not an illusion or a trick of perception. Time genuinely flows at different rates in different locations. A clock on the surface of the Earth ticks slightly slower than a clock on a satellite in orbit. The difference is tiny, only about 7 microseconds per day, but it is real and measurable. GPS satellites have to correct for this effect, or they would accumulate errors of several kilometers per day. Near a black hole, this time dilation becomes extreme. As you approach the event horizon, time, as measured by a distant observer, slows down more and more. At the event horizon itself, time dilation becomes infinite. This creates one of the strangest paradoxes in all of physics, something called the frozen star problem. Imagine you are watching a friend fall toward a black hole. As they get closer and closer to the event horizon, you see them moving slower and slower. The light coming from them becomes more and more redshifted, stretched to longer wavelengths by the extreme gravitational field. They appear to freeze just above the event horizon, their image becoming dimmer and redder, fading from visible light to infrared to radio waves, until finally they disappear from view entirely. But here is the paradox. From your friend's perspective, nothing special happens at the event horizon. They do not slow down. They do not feel anything unusual. They sail right through the event horizon and continue falling inward. Their watch ticks at the same rate it always has. To them, only a finite amount of time passes before they cross the horizon. So, which is it? Does your friend cross the horizon or not? The answer is both. This is not a contradiction. It is a consequence of the fact that space-time itself is curved near a black hole. Your friend and you inhabit different reference frames, different slices through the four-dimensional fabric of space-time. From your external viewpoint, your friend approaches the horizon asymptotically, taking infinite time to actually cross it. From their viewpoint, they cross it in a finite time. Both perspectives are equally valid. This is similar to asking whether a road trip takes 3 hours or 200 miles. The question does not make sense because hours and miles are different types of measurements. Similarly, asking whether an event takes a finite or infinite amount of time does not have a single answer. It depends on who is measuring. This has profound implications. It means that, from the perspective of an outside observer, nothing ever actually enters a black hole. Everything that has ever fallen toward a black hole is still there, frozen at the event horizon, taking infinite time to cross. From the perspective of the infalling matter, however, the event horizon is crossed quickly and without ceremony. This dichotomy will become important when we discuss the information paradox and the firewall controversy. But for now, let us continue with our understanding of black hole structure. Most black holes in the universe are not as simple as the spherical, non-rotating Schwarzschild solution. Real black holes form from the collapse of rotating stars, and they inherit that rotation. A rotating black hole is described by a different solution to Einstein's equations, discovered by Roy Kerr in 1963. Kerr black holes have all the features of Schwarzschild black holes, but with added complexity. The singularity is no longer a point, but a ring. There is a region outside the event horizon called the ergosphere where spacetime itself is dragged around the black hole, a phenomenon called frame dragging. Inside the ergosphere, it is impossible to remain stationary. Spacetime itself is flowing around the black hole like a whirlpool, and you are dragged along with it. This has fascinating consequences. It means that energy can, in principle, be extracted from a rotating black hole through a process called the Penrose process. If you drop an object into the ergosphere and arrange for it to split in just the right way, one piece can fall into the black hole while the other escapes with more energy than the original object had. The extra energy comes from the rotational energy of the black hole itself, which spins down slightly in the process. This is not just theoretical. Some astronomers believe that the enormous jets of matter and energy that we see shooting out from the centers of active galaxies are powered by this mechanism, extracting rotational energy from supermassive black holes. The existence of the ergosphere and frame dragging has been confirmed around Earth itself. In 2004, the Gravity Probe B satellite measured the tiny amount of frame dragging caused by Earth's rotation. Near a rotating black hole, this effect becomes millions of times stronger. There is another feature of Kerr black holes worth mentioning, something called the Cauchy horizon. In addition to the event horizon, rotating black holes have an inner horizon, beyond which the structure of spacetime becomes unstable. This inner horizon is a boundary where, theoretically, tiny quantum fluctuations could be amplified to macroscopic scales, potentially creating a firewall of high-energy particles or causing spacetime itself to become undefined. Whether the Cauchy horizon exists in real black holes, or whether quantum effects smooth it out or prevent it from forming is still debated. It is one of many questions that can only be answered by a theory of quantum gravity, which we do not yet have. Now, you might be wondering, if black holes trap everything including light, how did we ever discover them? How do we know they exist? The answer is that while we cannot see black holes directly, we can see their effects on nearby matter. When a black hole is part of a binary system with a normal star, it can pull matter away from its companion. This matter does not fall straight into the black hole, but forms a swirling disk around it called an accretion disk. As the matter spirals inward, it heats up due to friction and gravitational compression, reaching temperatures of millions of degrees. At these temperatures, it emits intense X-rays, which we can detect with space-based telescopes. The first black hole candidate, Cygnus X1, was discovered this way in 1964. Astronomers noticed an intense X-ray source in the constellation Cygnus. When they looked at that location with optical telescopes, they found a blue supergiant star that seemed to be orbiting an invisible companion. By measuring the motion of the visible star, they could calculate the mass of the invisible object. It was about 15 times the mass of the Sun, far too heavy to be a neutron star, the only other known type of compact object. It had to be a black hole. Since then, we have discovered thousands of black hole candidates using similar techniques. But the most convincing evidence came in 2015, when the LIGO Gravitational Wave Observatory detected the merger of two black holes. As these two objects spiraled into each other, they created ripples in spacetime itself that propagated outward at the speed of light. When those ripples reached Earth, they caused the mirrors in LIGO's 4-kilometer-long arms to shift by a distance smaller than the width of a proton. From that tiny signal, physicists could reconstruct the entire event. Two black holes, one about 36 times the mass of the Sun, and the other about 29 solar masses, spiraling together over the course of a fraction of a second, merging into a single black hole of about 62 solar masses. The missing 3 solar masses, a mass equivalent to 3 entire stars, was converted directly into gravitational wave energy according to Einstein's famous equation. The energy released in that fraction of a second was greater than the combined light output of every star in the observable universe. Since that first detection, LIGO and its European counterpart Virgo have detected dozens of black hole mergers, confirming beyond any doubt that these objects are real and relatively common. But the most visually stunning evidence came in April 2019, when the Event Horizon Telescope collaboration released the first direct image of a black hole. The target was the supermassive black hole at the center of the galaxy Messier 87, located about 55 million light-years from Earth. This black hole contains about 6.5 billion times the mass of the Sun, making it one of the most massive black holes known. To image it, astronomers linked 8 radio telescopes spread across the Earth, from Hawaii to Chile to Antarctica, creating a virtual telescope the size of our planet. The image showed exactly what Einstein's equations predicted: a dark circular region, the shadow of the event horizon, surrounded by a bright ring of glowing gas. The shadow is not the event horizon itself, but rather the photon sphere, a region just outside the event horizon where light can orbit the black hole. Any light emitted from inside this region either falls into the black hole or escapes to infinity. The boundary between these two fates creates the shadow we see. 2 years later, in May 2022, the same team released an image of Sagittarius A star, the supermassive black hole at the center of our own Milky Way galaxy. At 4 million solar masses, it is much smaller than the one in M87, but it is also much closer, only about 27,000 light-years away. Again, the image matched predictions perfectly. These images are remarkable achievements, but they show us only the outside of a black hole. The event horizon itself remains invisible, and the interior is forever hidden. Which brings us to the question we have been building toward. What would happen if you actually fell into one of these things? Before we can answer that, we need to understand one more crucial concept: the nature of information and why its fate inside black holes has become one of the biggest controversies in modern physics. In physics, information is a well-defined concept. It refers to the complete quantum state of a system, every detail about every particle. A fundamental principle of quantum mechanics is that information is never destroyed. You can scramble it, encrypt it, spread it out, but it can always, in principle, be recovered. If you burn a book, the information in that book is not destroyed. It is converted into smoke, ash, and heat radiation. An impossibly advanced civilization with perfect knowledge of every particle could, in principle, reconstruct the book from that smoke and ash. This principle, conservation of information, is as fundamental to quantum mechanics as conservation of energy is to classical physics. Now, here is the problem. What happens to the information about matter that falls into a black hole? According to general relativity, it crosses the event horizon and eventually hits the singularity where it is destroyed, gone, permanently. This would violate quantum mechanics. In 1974, Stephen Hawking made this problem even worse. He discovered that black holes are not entirely black. Due to quantum effects near the event horizon, black holes emit thermal radiation, now called Hawking radiation. Here is how it works. In quantum field theory, empty space is not really empty. Virtual particle-antiparticle pairs are constantly popping into existence and annihilating each other. This happens everywhere, all the time, but normally these virtual particles live for such a short time that they have no observable effect. Near the event horizon of a black hole, something different can happen. If a particle-antiparticle pair appears right at the horizon, one particle might fall into the black hole while the other escapes. To an outside observer, it looks like the black hole has emitted a particle. But particles carry energy, and that energy has to come from somewhere. It comes from the black hole itself, which loses a tiny amount of mass each time a particle escapes. Over time, the black hole evaporates. For a black hole with the mass of the Sun, this process would take about 10 to the power of 67 years, far longer than the current age of the universe. But for a tiny black hole, say the mass of a mountain, it would evaporate much faster, ending in a violent explosion of radiation. Now, here is the paradox. Hawking radiation is thermal, meaning it is completely random, containing no information about what fell into the black hole. It is like the heat from a fire, which tells you nothing about what was burned. So, if a black hole eventually evaporates completely, converted entirely into random thermal radiation, what happened to the information about everything that fell in? It seems to have been destroyed, violating quantum mechanics. This is the black hole information paradox, and it has been the subject of intense debate for 50 years. Hawking initially believed that information was indeed destroyed, that black holes represented the first and only exception to the laws of quantum mechanics. Many physicists disagreed, most notably Leonard Susskind, who engaged in a decades-long debate with Hawking about this issue. In 2004, Hawking conceded that information must somehow be preserved, though exactly how remains unclear. One possibility is that the information is somehow encoded in the Hawking radiation in a way that is too subtle for us to currently understand. Another is that it is stored at the event horizon itself, encoded in microscopic quantum details of the horizon's structure. This leads to an idea called the holographic principle, which suggests that all the information about the three-dimensional interior of a black hole is encoded on its two-dimensional surface, like a hologram. This principle has had profound implications far beyond black holes, suggesting that the same might be true of the entire universe. Perhaps all of three-dimensional reality is actually information encoded on a two-dimensional boundary at the edge of the cosmos. This is highly speculative, of course, but it is grounded in serious theoretical work and has become a major research program in theoretical physics. The information paradox has recently spawned an even more controversial idea called the firewall paradox. In 2012, a group of physicists led by Ahmed Amheri, Donald Maroff, Joseph Polchinski, and James Sully, collectively known as AMPS, argued that if information is preserved, then there must be a firewall of extremely high-energy particles right at the event horizon. Here is the logic. If the information about matter that fell into a black hole long ago is now coming out in Hawking radiation, then that radiation must be quantum mechanically entangled with the matter inside. But Hawking's calculation also shows that the radiation must be entangled with particles near the horizon. Quantum mechanics does not allow a particle to be maximally entangled with two different things at once. So something has to give. Either information is destroyed after all, or the horizon is not the smooth, empty place that general relativity says it should be. Instead, it is a seething wall of high-energy particles, a firewall that would instantly incinerate anything trying to cross. This contradicts a principle called black hole complementarity, proposed by Susskind, which says that an infalling observer should experience nothing special at the horizon. The firewall paradox remains unresolved. Some physicists believe that firewalls are real, others that there is some subtle error in the AMPS argument that allows information to be preserved without firewalls. Still, others believe that the paradox is revealing something fundamental about the nature of spacetime itself, that perhaps spacetime is not a fundamental entity, but rather emerges from more basic quantum information. These are deep waters, and we have only dipped our toes in. The point is that even the event horizon, the mere boundary of a black hole, is surrounded by profound mysteries. And we have not even crossed it yet. So let us take that final step. Let us cross the event horizon and journey into the interior of a black hole. What would you experience? What would you see? And what would ultimately happen to you? That is where we will go next, but before we do, we need to address one more crucial question. How different is falling into a stellar mass black hole versus falling into a supermassive one? The answer is dramatic. It is the difference between instant obliteration and a surprisingly gentle experience, at least initially. The key is tidal forces. Gravity does not pull uniformly on your body. Your feet, being closer to the black hole than your head, experience a slightly stronger gravity. This difference creates a stretching force. For a stellar mass black hole of 10 solar masses, with an event horizon about 30 kilometers in radius, the tidal forces at the event horizon are enormous. Long before you reach the horizon, the difference in gravitational pull between your head and feet would be enough to tear you apart at the molecular level. The process has been whimsically termed spaghettification, as you would be stretched into a long, thin strand. For a supermassive black hole, the situation is completely different. The Schwarzschild radius scales linearly with mass. A black hole 1,000,000 times more massive has an event horizon 1,000,000 times larger. But tidal forces scale inversely with the square of the distance to the center. This means that for a sufficiently massive black hole, the tidal forces at the event horizon can be less than what you experience standing on Earth right now. For Sagittarius A star at the center of our galaxy, you could cross the event horizon without even noticing. You would not be spaghettified until much later, deep inside, as you approached the singularity. This difference is crucial for our journey. If we want to explore the interior of a black hole, we need to choose a supermassive one. So let us imagine falling into something truly gigantic, a black hole of 1 billion solar masses. Its event horizon would be about 3 billion kilometers in radius, roughly the distance from the Sun to Uranus. At this scale, the tidal forces at the horizon would be negligible. You could cross in comfort, at least initially, so you are falling inward, accelerating under the pull of gravity, approaching the event horizon of this monster. What do you see? The view would be spectacular and bizarre. Due to gravitational lensing, the black hole would bend light around it. creating multiple distorted images of the stars behind it. As you got closer, you would see these distorted images wrapping around the black hole, the entire universe appearing to compress into a bright ring in front of you. Behind you, the view would darken as light struggled to reach you from that direction. If you looked carefully, you might see the photon sphere, a glowing ring where light is orbiting the black hole. Any light emitted from this region is trapped in unstable orbits, circling the black hole multiple times before either falling in or escaping. As you crossed the event horizon, you might expect something dramatic to happen, but there would be nothing. No flash of light, no sensation, no boundary marker. Just endless darkness ahead and the compressed, brightening universe behind. This is one of the most unsettling aspects of crossing the event horizon. From your perspective, nothing changes. Space looks the same. Time flows the same. Your instruments show no anomaly. The only indication that something has changed is that you can look back and see the universe outside, but the universe outside can no longer see you. You have crossed into a region of space-time from which there is no return, and you did not even notice. Welcome to the interior of a black hole. You have crossed the event horizon, and for a few moments, everything seems almost normal. Your body feels no different. Your spacecraft, if you brought one, continues to function. The air pressure, temperature, gravitational pull on your feet, all of it is exactly what it was a moment ago. This is deeply counterintuitive because crossing the event horizon feels like it should be momentous, like stepping through a portal or breaking through a barrier. But event horizons are not physical things. They are mathematical surfaces, places where the geometry of spacetime takes on a particular configuration. There is nothing there to touch, nothing to feel. If you had not been carefully tracking your position, you might not even realize you had crossed. But something profound has changed, something that will only become apparent when you try to communicate with the outside universe or when you try, futilely, to turn around. Let us talk about what has actually happened to you in terms of the structure of spacetime. In ordinary space, you are free to move in any direction. You can go forward or backward, left or right, up or down. The future is the direction time flows, toward tomorrow, next week, next year. The past is behind you, yesterday, last month, last year. These directions are fundamentally different. You can move freely through space, but only forward through time. Inside a black hole, this distinction breaks down in a very specific way. The singularity at the center of the black hole is not a place in space. It is a moment in time. Specifically, it is a moment in your future. Just as you cannot avoid reaching next Tuesday by moving left or right, you cannot avoid reaching the singularity by changing your spatial position. Every direction you point, every thrust you fire from your engines, all of it only determines where you hit the singularity, not whether you hit it. The singularity is not south of you or below you or in front of you. It is in your future, as inevitable as tomorrow. This is what physicists mean when they say that inside a black hole, space and time swap roles. Outside the black hole, the radial direction, toward or away from the center, is a spatial direction you can move through freely. The time direction is fixed, always forward. Inside the black hole, the radial direction becomes time-like, flowing inexorably inward, while some of the time directions become space-like, offering a kind of spatial freedom. To visualize this, imagine a diagram where we plot time vertically and space horizontally. Outside the black hole, your light cone, the set of all possible futures you could reach, points upward into the future. You can go left or right, but you always go forward in time. At the event horizon, your light cone tips over. Inside the event horizon, your light cone points inward, toward the singularity. Every possible future you could reach, firing your engines in any direction, waiting, accelerating, All of them lead to the singularity. Not because something is pulling you there, though gravity is certainly part of the story, but because the singularity is in the direction that time flows. Asking how to avoid the singularity once you are inside the event horizon is like asking how to avoid next Thursday. You cannot. It is not a matter of propulsion or cleverness. It is a consequence of the causal structure of space-time itself. Now, how much time do you have? How long before you reach the singularity? For a Schwarzschild black hole, a non-rotating one, the answer is straightforward to calculate. Once you cross the event horizon, it takes about 15 microseconds per solar mass of the black hole to reach the singularity. For our billion solar mass black hole, that works out to about 4 hours. 4 hours from the moment you cross the horizon to the moment you are destroyed. For a stellar mass black hole of 10 solar masses, you would have less than 1/10 of a second. This is why choosing a supermassive black hole is essential if we want to explore the interior. You need time, and time is one thing the universe inside a black hole has in very limited supply. So you have about 4 hours. What happens during that time? Let us start with what you see. Behind you, if you look back toward where you came from, you can still see the outside universe. Light from outside can still reach you because it is also falling inward. But that view is changing rapidly. Due to the extreme curvature of space-time, light from the outside is blue-shifted to shorter wavelengths. Stars that were red now look yellow. Yellow stars look blue. The cosmic microwave background radiation, normally invisible microwaves, is shifted into visible light. If you could see it, it would look like a faint glow. As you fall deeper, this blue shifting becomes more extreme. The outside universe appears to brighten and speed up. Days and years appear to pass in seconds as time dilation works in reverse from your perspective now. You are the one moving rapidly through time, relative to the outside universe. What is ahead of you, deeper into the black hole, is pure darkness. No light has ever escaped from deeper inside, so there is nothing to see. You are falling into an abyss that has never been illuminated. If you brought a flashlight, you could shine it around, and you would see the interior of your spacecraft or your spacesuit, but beyond that, nothing. The light from your flashlight spreads outward, but because space-time is curved, even light moving away from the singularity is actually getting closer to it in terms of the distance it will eventually travel. Shine your light backward toward the event horizon you just crossed, and it will never reach it. It will curve around and eventually fall into the singularity, just like you. Now, let us talk about tidal forces, because this is what will eventually kill you. Even in our supermassive black hole, where tidal forces at the event horizon were negligible, they grow stronger as you approach the singularity. Remember, tidal forces arise because gravity is stronger closer to the source. The difference in gravitational pull between your head and your feet might have been tiny at the horizon, but it grows rapidly as you fall inward. The mathematics of tidal forces is straightforward. The tidal acceleration scales inversely with the cube of the distance to the center. If you are twice as close, the tidal force is 8 times stronger. As you fall from the event horizon toward the singularity, getting closer and closer to the center, the tidal forces grow without bound. At some point, they will exceed the tensile strength of your body. Your feet will be pulled away from your legs from your torso. Your torso will be stretched into a thin strand. Then your cells will be pulled apart. Then your molecules. Then your atoms. Eventually, even atomic nuclei will be ripped apart, and you will be reduced to a stream of elementary particles, all stretched along a radial line pointing toward the singularity. This process is called spaghettification, a term coined by Stephen Hawking, and it is the ultimate fate of anything that falls into a black hole. The only question is when it happens. For our billion solar mass black hole, spaghettification would not begin until you were quite close to the singularity, perhaps in the final minutes of your 4-hour journey. For a stellar mass black hole, it would happen long before you even reached the event horizon. There is another effect worth mentioning, though it is much more subtle. As you fall inward, different parts of your body are moving through space-time at slightly different rates. Your feet are ahead of your head in time, in a sense. This means that your feet are experiencing the future slightly before your head does. For a human-sized object in any realistic black hole, this effect is negligible compared to the tidal stretching. But it is there, a consequence of the warped geometry. Now, everything we have discussed so far assumes a Schwarzschild black hole, one that is perfectly spherical and not rotating. Real black holes are not like this. They are formed from the collapse of rotating stars, and they inherit that rotation. A rotating black hole is described by the Kerr solution, and its interior is far stranger than the Schwarzschild case. The singularity of a Kerr black hole is not a point, but a ring. If you could somehow visualize it, it would look like a loop of infinitely dense matter, or rather, a loop where the curvature of spacetime becomes infinite. This ring singularity lies in the plane of rotation, and its radius depends on how fast the black hole is spinning. For a maximally rotating black hole, called an extremal Kerr black hole, the ring is as large as the event horizon itself. For slower rotation, it is smaller. The existence of a ring singularity opens up bizarre possibilities. In the Schwarzschild case, all paths lead to the point singularity. There is no way around it. But in the Kerr case, it is mathematically possible to pass through the ring. The Kerr solution, as a mathematical structure, actually extends beyond the ring singularity into a region of negative radius, whatever that means, which connects to another universe or another region of spacetime with very strange properties. Some solutions even show that you could pass through the ring and emerge into a region where the singularity is in your past, not your future, meaning you could avoid it. This has led to speculation about using rotating black holes as portals to other universes, or even as time machines. Unfortunately, this is almost certainly not possible in reality. The problem is stability. The inner structure of a rotating black hole includes something called the Cauchy horizon, an inner boundary inside the event horizon. At the Cauchy horizon, the geometry of spacetime becomes extremely unstable. Any small perturbation, a single photon of light, a quantum fluctuation, gets amplified enormously. Calculations suggest that the Cauchy horizon would be a place of infinite energy density, a region where the curvature of spacetime diverges. This is sometimes called the mass inflation instability. As you approach the Cauchy horizon, you would encounter a wall of infinitely blue-shifted radiation, the accumulated light from the entire history of the universe outside, compressed into a single moment. This would destroy anything trying to pass through. Even worse, the presence of this instability suggests that the classical Kerr solution breaks down at the Cauchy horizon. Quantum effects, which we have been ignoring, would become important, and we do not have a theory of quantum gravity to tell us what happens. It is possible that quantum effects smooth out the Cauchy horizon, preventing the divergence. It is also possible that they make it worse, creating a firewall of high-energy particles. Or perhaps something even stranger happens that we cannot currently predict. The upshot is that while the mathematics of the Kerr solution allows for traversable paths through a rotating black hole, the physics almost certainly does not. Any realistic rotating black hole would have an interior that is just as lethal, just as inescapable as the Schwarzschild case, and probably more chaotic. There is another feature of rotating black holes worth discussing: the ergosphere. The ergosphere is a region outside the event horizon where spacetime is dragged around the black hole by its rotation. Inside the ergosphere, it is impossible to remain stationary. You are forced to move in the direction of the black hole's rotation, dragged along by spacetime itself. This is called frame dragging, and it has been measured around Earth, albeit very weakly. Near a rotating black hole, frame dragging becomes extreme. Inside the ergosphere, spacetime is rotating faster than the speed of light in some sense, though this does not violate relativity because it is spacetime itself that is moving, not matter or light moving through spacetime. The boundary of the ergosphere is called the stationary limit because it is the innermost point where you can remain stationary relative to distant stars. Inside that boundary, you must orbit the black hole, or fall inward. This has an interesting consequence. It means that energy can be extracted from a rotating black hole. In 1969, Roger Penrose showed that if you drop an object into the ergosphere and arrange for it to split in just the right way, one piece falling into the black hole and the other escaping, the escaping piece can have more energy than the original object. The extra energy comes from the rotational energy of the black hole, which spins down slightly. This is called the Penrose process, and it is believed to be the mechanism behind some of the most energetic phenomena in the universe. When a black hole accretes matter, that matter forms a disk around it. Magnetic fields threading through the disk can tap into the rotational energy of the black hole, extracting energy and flinging it outward as powerful jets. These jets can extend for hundreds of thousands of light years and shine with the luminosity of trillions of suns. The energy source is the black hole's rotation, slowly draining away through the Penrose process. But we are getting distracted by what happens outside the black hole. Let us return to the interior. You are falling inward, the tidal forces are growing stronger, and the singularity is in your future, unavoidable. What else is there to say about your journey? One aspect we have not discussed is what happens to light and other particles inside the black hole. You are not alone in this fall. Anything else that crossed the event horizon before you is also falling inward. Light that entered the black hole seconds or centuries ago is still here, all of it spiraling inward toward the singularity. In principle, you could see light from objects that fell in long before you did, assuming it has not yet reached the singularity. If a star fell into this black hole 1,000 years ago, some of the light from that star might still be inside, falling inward alongside you. You could see it, a ghost of the past, doomed like you. There is also the Hawking radiation to consider, though its effects inside the black hole are not well understood. Hawking radiation is produced at the event horizon by quantum effects, and it carries energy away from the black hole. But from the perspective of someone inside, what does this mean? Does the event horizon glow with radiation? Is there a subtle flux of particles appearing at the horizon? The honest answer is that we do not know. Hawking's original calculation was done from the perspective of an outside observer, and does not tell us what an infalling observer would see. Some theories suggest that the horizon would appear to be a firewall, a wall of high-energy particles, though this is controversial. Others suggest it would appear completely empty and dark, just as general relativity predicts. This is one of many questions that can only be answered by a theory of quantum gravity. Another question is what happens to information about your quantum state as you fall inward. We discussed the information paradox earlier, the question of whether information is destroyed in a black hole or somehow preserved. From your perspective inside the black hole, you are still carrying that information. You exist. Your quantum state is well defined. But from the perspective of an outside observer, your information must be encoded in the Hawking radiation that the black hole emits over its lifetime. How can both be true? One proposed resolution is black hole complementarity. The idea is that the information is both inside the black hole, from your perspective, and encoded on the event horizon, from an outside perspective, and that these two descriptions never contradict each other because no single observer can verify both. You, falling in, see the information carried inward to the singularity. An outside observer sees it encoded on the horizon and eventually released in Hawking radiation. Because you can never communicate your observations to the outside observer after crossing the horizon, there is no contradiction. This is a deeply strange idea. It suggests that the same information exists in two places at once, that reality is described by two different, incompatible stories, and that both are true. It is like the observer paradox in quantum mechanics taken to an extreme. Whether black hole complementarity is correct is still debated. The firewall paradox, which we discussed earlier, challenges it by arguing that the two descriptions cannot both be right. If information is encoded on the horizon and in the Hawking radiation, then the interior must be different from what general relativity predicts. It must contain a firewall that destroys anything trying to enter. If there is no firewall, then information must be lost, or some other principle must be violated. This is an active area of research, with no consensus yet. What is clear is that black holes are forcing us to reconsider our most basic assumptions about information, space-time, and the nature of reality itself. Let us return to your journey. You have been falling for hours now, and the tidal forces are becoming severe. Your spacecraft, if you had one, has long since been torn apart. You are being stretched into a thin strand of matter, screaming silently in the vacuum. Well, perhaps there is no screaming at this point. Perhaps consciousness ended minutes ago, when your brain was stretched beyond the point where neurons could function. What is left of you is a stream of particles, still falling, still accelerating toward the singularity. The singularity is close now, and the tidal forces are approaching infinity. The curvature of space-time is becoming infinite. General relativity, the theory that has guided us this far, is breaking down. At some point, very close to the singularity, quantum effects must become important. The distance scales become so small, the energies so high, that we enter the realm of quantum gravity, a theory we do not yet have. What happens in those final moments? Does space-time end? Does it transform into something else? Does the singularity even exist? Or does quantum gravity prevent it from forming? These are the questions we will explore next, but before we do, let us take stock of what we have learned. Crossing the event horizon is surprisingly uneventful if the black hole is large enough. There is no barrier, no wall, no sudden transition. You simply pass from a region where escape is possible to a region where it is not. Once inside, your fate is sealed. The singularity is in your future, as inevitable as next Thursday. You have a finite amount of time, hours for a supermassive black hole, milliseconds for a stellar mass one, before tidal forces rip you apart. During that time, you can still see the outside universe, blue-shifted and speeding up, but you can never send a signal back. You are cut off, isolated in a pocket of space-time that is doomed to collapse to infinite density. If the black hole is rotating, the interior is even stranger. There is a ring singularity, an inner horizon, and theoretical paths that lead to other regions of space-time. But these paths are almost certainly blocked by instabilities, by walls of infinitely energetic radiation, or by quantum effects that we do not yet understand. And there are the paradoxes. The information paradox, which asks what happens to the quantum state of everything that falls in. The firewall paradox, which suggests that the event horizon might not be the smooth, empty place we thought. The complementarity principle, which suggests that reality itself has two contradictory descriptions, both equally true. All of these point to the same conclusion. Black holes are places where our current theories break down. General relativity predicts a singularity, a point where the curvature of space-time becomes infinite, where density becomes infinite, where the equations themselves give nonsensical answers like infinity and undefined. This is the theory telling us that it has reached its limits, that something beyond it is needed to describe what really happens. That something is quantum gravity, the holy grail of theoretical physics, the theory that unifies quantum mechanics and general relativity into a single framework. We do not have that theory yet, but we have clues, hints from string theory, loop quantum gravity, and other approaches about what it might look like. And one of the places where those clues are most valuable is the singularity at the center of a black hole. That is where we go next, into the final moments, the last microseconds before you reach the point where classical physics ends and quantum gravity begins. What awaits you there? What replaces the singularity? Is there a bounce, a tunnel to another universe, a transformation into something we cannot currently imagine? Let us find out. You are approaching the singularity. The tidal forces have grown so extreme that you no longer exist as a coherent structure. What was once a human body, or a spacecraft, or any organized system of matter, has been reduced to a stream of elementary particles stretched along a radial line. Each particle is following its own trajectory through spacetime, but all trajectories converge on the same point in the future. The singularity. According to general relativity, the singularity is a point where the curvature of spacetime becomes infinite. Density becomes infinite. Temperature becomes infinite. All the matter that has ever fallen into this black hole, every atom from every star, every particle of gas, every photon of light, all of it is compressed into a single point of zero volume. This is what the mathematics says. But infinity is not a number. It is not a physical quantity. When a theory predicts infinity, it is telling you that the theory has broken down, that it can no longer describe what is happening. It is like dividing by zero on a calculator. The calculator does not give you a meaningful answer because the question itself has taken you outside the domain where the rules apply. General relativity is that calculator, and the singularity is the place where we have asked it to divide by zero. So what really happens at the singularity? The honest answer is that we do not know. We need a theory of quantum gravity to describe it, and we do not have such a theory yet. But we have clues. We have partial theories, speculative ideas, and mathematical frameworks that give us hints about what might replace the classical singularity. Let us explore them. The first and most important clue comes from the nature of quantum mechanics itself. In quantum mechanics, there is a fundamental limit to how small and how precise things can be. This limit is set by the Planck scale, named after Max Planck, one of the founders of quantum theory. The Planck length is about 10 to the minus 35 meters, or about a trillion times smaller than an atomic nucleus. The Planck time is about 10 to the minus 43 seconds, the time it takes light to cross a Planck length. At these scales, quantum fluctuations in spacetime itself become important. Spacetime can no longer be treated as a smooth continuum, but must be thought of as something foamy, grainy, uncertain. The very notions of distance and duration become fuzzy. Many physicists believe that the singularity predicted by general relativity is replaced by some kind of quantum structure at the Planck scale. Instead of compressing to a point of infinite density, matter might compress only to the Planck density, which is enormous but finite. At this density, a single cubic centimeter would contain about 10 to the 93 grams, or about 1 billion times the mass of the observable universe compressed into the volume of a sugar cube. This is absurdly dense, but it is not infinite. What could prevent further collapse? What could provide the pressure to resist gravity at these extreme densities? One possibility comes from a principle called quantum pressure. In quantum mechanics, particles cannot be localized to arbitrarily small regions of space. The more you try to confine a particle, the more its momentum becomes uncertain and the more energy it has. This is the Heisenberg uncertainty principle. When you try to compress matter to very small volumes, this quantum uncertainty creates an effective pressure that resists further compression. This is what supports white dwarf stars against their own gravity. When a star runs out of fuel and collapses, electrons are packed so tightly that their quantum pressure, called electron degeneracy pressure, holds the star up. If the star is too massive, gravity overcomes electron degeneracy pressure, and the star collapses further. Electrons are crushed into protons, forming neutrons, and you get a neutron star supported by neutron degeneracy pressure. If the star is even more massive, gravity overcomes neutron degeneracy pressure, and according to classical theory, nothing can stop the collapse. You get a black hole with a singularity. But at the Planck scale, quantum effects of spacetime itself might provide the ultimate form of degeneracy pressure. Spacetime itself might resist being compressed beyond the Planck density. This leads to an idea called a Planck star. Instead of a singularity at the center of a black hole, there might be a tiny core of matter compressed to the Planck density, held up by quantum gravitational pressure. This Planck star would be incredibly small, far smaller than an atomic nucleus, but it would not be a singularity. It would be a physical object with finite size and density. If this is correct, then the interior of a black hole would not end at a singularity, but at a tiny core. But what happens when you reach this core? Do you just sit there, compressed to unimaginable density but not infinite density, for the rest of time? Some models suggest something even stranger, a bounce. The idea is that quantum gravitational effects do not just stop the collapse, but reverse it. The Planck star would not be static, but would bounce back, expanding outward. Of course, this bounce cannot push outward through the event horizon into our universe. That is still forbidden by the causal structure of spacetime. Instead, the bounce might create a new region of spacetime, potentially even a new universe, connected to our universe through the black hole. This is highly speculative, but it is based on serious work in loop quantum gravity, one of the leading approaches to quantum gravity. In loop quantum gravity, spacetime is not continuous but is made of discrete chunks, tiny loops, and nodes that form a kind of quantum fabric. When you try to compress spacetime beyond the Planck scale, the quantum structure prevents it. The equations of loop quantum gravity applied to black holes suggest that the singularity is replaced by a high curvature region where a bounce occurs. Some researchers have gone further and suggested that every black hole in our universe might give birth to a new universe through this bounce mechanism. In this picture, our own universe might have been born from the interior of a black hole in some parent universe. This is called cosmological natural selection, an idea proposed by physicist Lee Smolin. It is a fascinating speculation, but it is important to emphasize that we have no observational evidence for it. It is a prediction of some quantum gravity models, but we cannot test it directly because we cannot see inside black holes or communicate with hypothetical universes born from them. Let us turn to another approach, string theory. String theory proposes that the fundamental constituents of nature are not point particles, but tiny vibrating strings of energy. Different vibration patterns correspond to different particles: electrons, quarks, photons, and so on. One of the remarkable features of string theory is that it naturally includes gravity. A particular vibration pattern of a string corresponds to a graviton, the hypothetical quantum particle of gravity. This means string theory is, in principle, a theory of quantum gravity. What does string theory say about black holes? In string theory, black holes are not empty spacetime with a singularity at the center. Instead, they are complex objects made of strings and higher dimensional membranes called branes, all vibrating in intricate patterns. The information about what fell into the black hole is stored in the arrangement and vibration of these strings. This is the fuzzball proposal. According to this idea, If you could zoom in on a black hole with perfect resolution, you would not see an event horizon with empty space inside. You would see a fuzzy ball of strings filling the entire volume out to what we call the event horizon. There is no interior, no singularity. The black hole is the strings. The event horizon is not a real surface, but an effective description that emerges when you view the fuzzball from far away. From a distance, the fuzzball looks like a black hole with an event horizon. But up close, it is a dense tangle of quantum strings. This solves the information paradox in an elegant way. Information is not destroyed because it never falls into a separate interior region. It is always part of the fuzzball, encoded in the string configuration. When the black hole evaporates through Hawking radiation, the information is released as the strings gradually decay. The fuzzball idea is beautiful, but it is also controversial. One problem is that it seems to contradict the equivalence principle, a cornerstone of general relativity. The equivalence principle says that free fall is indistinguishable from floating in empty space. If you are in a windowless room, you cannot tell whether you are floating in deep space or falling freely under gravity. Applied to black holes, this means that crossing the event horizon should feel like passing through empty space. There should be nothing special there, no structure, no fuzziness. But if the fuzzball picture is correct, the event horizon is not empty. It is filled with strings. This means that crossing the horizon would not be smooth. You would encounter the strings, and that would be measurable, at least in principle. This brings us back to the firewall paradox. If the horizon is not empty, if there is structure there, then that structure might be energetic enough to destroy anything trying to cross. This would be the firewall. The firewall would solve the information paradox by preventing anything from ever actually entering the black hole. But it would violate the equivalence principle. You would feel something special at the horizon. Different string theorists have different views on this. Some embrace the fuzzball and argue that the equivalence principle must be modified. Others argue that the fuzzball structure is real, but is arranged in such a way that it does not violate the equivalence principle in any observable way. The strings might be there, but they are in a quantum state that appears empty to an infalling observer. Still others believe that the firewall paradox points to a deeper issue, that our understanding of spacetime and quantum mechanics is incomplete in some fundamental way. There is another approach to quantum gravity worth mentioning: causal set theory. In this framework, spacetime is not a smooth continuum or even a network of loops, but a discrete set of events with causal relationships between them. The structure of spacetime emerges from these causal relations. Applied to black holes, causal set theory suggests that the singularity might be replaced by a region where the causal structure becomes extremely dense and complex, but not infinite. The details are still being worked out, but the general idea is that quantum discreteness prevents the formation of a true singularity. What all of these approaches have in common is the idea that the singularity is not real. It is an artifact of treating spacetime as perfectly smooth and continuous, which is an approximation that breaks down at extreme scales. When you account for the quantum nature of gravity, the singularity is replaced by something else: a Planck star, a fuzzball, a causal set, or some other quantum structure. But here is the problem. We do not know which, if any, of these ideas is correct. We do not have a complete theory of quantum gravity. String theory is mathematically rich, but has not made any testable predictions that distinguish it from other theories. Loop quantum gravity is more conservative, but also less developed. Causal set theory and other approaches are even more speculative. Without experimental data, we are essentially guessing, and experimental data is extraordinarily hard to come by. The Planck scale is so small, and the energies involved are so high that we cannot probe it directly with any conceivable particle accelerator. To probe the Planck scale directly, you would need an accelerator the size of the galaxy. Black holes are, in a sense, natural Planck-scale laboratories. The conditions near a singularity are exactly the conditions where quantum gravity should be important. But we cannot observe those conditions because they are hidden behind an event horizon. This is where the cosmic censorship hypothesis comes in. Proposed by Roger Penrose in 1969, the cosmic censorship hypothesis states that singularities are always hidden inside event horizons. Nature, in other words, is modest. She does not allow naked singularities, singularities that are visible from the outside universe. If cosmic censorship is true, then we can never observe the Planck scale physics near a singularity. It is always behind an event horizon, inaccessible to us. This means we can never test our quantum gravity theories by looking at black holes from the outside. We can only theorize and hope that someday we develop the mathematical tools to make clear predictions. There is one possible exception: Hawking radiation. If black holes evaporate completely, then at the very end of their life, the event horizon shrinks away, and the final moments might reveal the quantum structure inside. For a stellar mass black hole, this would take about 10 to the 67 years, far longer than the current age of the universe. But tiny primordial black holes, if they exist, could be evaporating right now. A black hole with the mass of a mountain would evaporate in about the age of the universe and would end in a violent explosion of gamma rays. No such explosions have been detected, which puts limits on how many tiny black holes there can be. But if one were to explode nearby, we might be able to learn something about the quantum structure that replaces the singularity. Let us shift our focus to the different types of singularities. We have been talking mostly about the Schwarzschild singularity, which is a point. But rotating black holes have ring singularities, and the structure is quite different. In the Kerr solution, the singularity is a one-dimensional ring lying in the equatorial plane of the black hole. If you were falling into a rotating black hole, you might not hit the ring directly. Depending on your trajectory, you could, in principle, pass through the ring. What would you find on the other side? The mathematics of the Kerr solution says that passing through the ring takes you to a region with negative radius, which is difficult to interpret physically. Some solutions connect to another universe or another region of spacetime with bizarre properties. In some of these regions, closed time-like curves exist, loops in spacetime that allow travel to your own past. This has led to speculation about using rotating black holes as time machines. Unfortunately, as we discussed earlier, these exotic regions are almost certainly unstable. The Cauchy horizon, the inner boundary you would cross before reaching the ring, is a place where tiny perturbations are amplified to infinite energy. Any realistic rotating black hole would have so much accumulated radiation and matter falling in that the Cauchy horizon would be a place of infinite energy density. You would be destroyed long before you could reach the ring singularity. Even if you somehow survived, quantum effects near the Cauchy horizon would likely destroy the exotic geometry predicted by the classical solution. Instead of a passage to another universe, you would find a wall of radiation or a chaotic region where spacetime breaks down. Still, it is fascinating that the mathematics allows for such possibilities. It suggests that the structure of spacetime is far richer and stranger than we might have imagined. Even if rotating black holes do not actually contain passages to other universes, the fact that the equations permit such things hints at deep connections between gravity, causality, and the topology of spacetime. There is also the question of charged black holes. In principle, a black hole could have an electric charge, and this would be described by the Reissner-Nordstrom solution if it is not rotating, or the Kerr-Newman solution if it is. Charged black holes have even stranger interiors than rotating ones. They have two event horizons, an outer and an inner, and a time-like singularity that you can, in principle, avoid. But charged black holes almost certainly do not exist in nature. Any charged black hole would quickly attract opposite charges from the surrounding environment and neutralize itself. Even if you somehow created a charged black hole in the lab, it would discharge in microseconds. So, while the mathematics of charged black holes is interesting, they are not physically realistic. The black holes we actually find in nature are probably well described by the Kerr solution: rotating, uncharged, and with a ring singularity surrounded by a Cauchy horizon that is probably unstable. Let us consider another question. What happens to different types of matter as they approach the singularity? We have been talking mostly about massive particles, things like atoms and spacecraft. But what about light? Photons also fall into black holes. Do they experience the singularity differently? In one sense, photons have it easy. Photons always travel at the speed of light, and from the perspective of a photon, no time passes at all. If a photon could experience time, it would be emitted and absorbed in the same instant, regardless of how far it traveled. So, from the photon's perspective, if we can even use that term, crossing the event horizon and reaching the singularity happens instantaneously. Of course, photons do not have a perspective. They do not experience time. But we can track the photon's path through spacetime, and that path is called a null geodesic. For a photon falling into a Schwarzschild black hole, the null geodesic ends at the singularity. The photon's journey is finite in terms of the proper time experienced by any massive observer who might be watching, but from the photon's own frame, the journey is instantaneous. What about more exotic particles, like neutrinos? Neutrinos are nearly massless and travel at very close to the speed of light. Their experience would be similar to photons, though not quite as extreme. They would fall in, strike the singularity, and be destroyed, all in a very short proper time. The interesting thing about neutrinos is that they interact very weakly with matter. A neutrino can pass through a light year of lead without being absorbed. But inside a black hole, there is no escape, even for neutrinos. The spacetime curvature is so extreme that no trajectory leads outward. Even particles that barely interact with anything are trapped. There is a deep philosophical question here about the nature of the singularity. When we say that matter is destroyed at the singularity, what do we mean? Is it annihilated, converted into energy, transformed into something else? The problem is that we do not have a framework to answer that question. General relativity says that the curvature becomes infinite, and that is where the theory stops. It does not tell us what happens to the matter. Quantum mechanics says that information cannot be destroyed, which suggests that the matter must persist in some form. But in what form? Is it encoded in quantum fluctuations of space-time? Is it converted into strings or loops or some other quantum structure? Is it tunneled to another universe? All of these are possibilities, but we do not have the tools to decide between them. This is why the singularity is such a profound mystery. It is not just a place where conditions are extreme. It is a place where our most fundamental theories break down, where the rules themselves cease to apply. It is a boundary of knowledge, a wall beyond which we cannot see with our current understanding of physics. And yet, the singularity might not even exist. Every approach to quantum gravity suggests that it is replaced by something else. If that is true, then the singularity is like the edge of the Earth on ancient maps. Early cartographers, lacking knowledge of the full globe, would draw the edge of the world and write, "Here be dragons." The singularity is our dragon, a placeholder for something we do not yet understand. Let us consider one more aspect of singularities, their role in the broader structure of the universe. Singularities are not just theoretical curiosities. They appear in other contexts in general relativity. The Big Bang, the origin of our universe, is also described by general relativity as a singularity. In the standard cosmological model, if you trace the expansion of the universe backward in time, everything converges to a single point of infinite density and temperature about 13.8 billion years ago. This initial singularity is similar in many ways to the singularity inside a black hole. Both are places where general relativity predicts infinite curvature and breaks down. Both require a theory of quantum gravity to describe properly. This has led some physicists to wonder whether there is a deeper connection. Could the Big Bang singularity be similar to the singularity inside a black hole? Could our universe have emerged from the interior of a black hole in some parent universe? This is the idea behind cosmological natural selection that we mentioned earlier. In this scenario, every black hole creates a new universe, and the parameters of physics in the new universe are slightly different from the parent. Universes that produce many black holes will have many offspring, while universes that produce few black holes will have few offspring. Over vast timescales, this could lead to a kind of evolution, selecting for universes with parameters that maximize black hole production. It is a beautiful idea, but it is also highly speculative. We have no way to test it, no way to observe these other universes or confirm that they exist. It is an example of how black holes push us to think about the deepest questions in cosmology and the nature of reality itself. Another connection between black holes and cosmology comes from the holographic principle. The holographic principle states that all the information contained in a volume of space can be encoded on the boundary of that volume. This idea originally came from studying black holes. The entropy of a black hole, a measure of how much information it contains, is proportional to the area of its event horizon, not its volume. This was a surprise. For ordinary objects, entropy is proportional to volume. A box twice as large can contain twice as many particles and twice as much information. But for black holes, it is the surface area that matters. This led physicists to propose that the same might be true for the universe as a whole. Perhaps all the information in our three-dimensional universe is encoded on a two-dimensional boundary, like a hologram. This has become a major research program in theoretical physics, with connections to string theory, quantum information, and the nature of spacetime itself. Black holes and the singularities they contain are not just astrophysical objects. They are windows into the deepest structure of reality, places where the normal rules break down and new principles emerge. They force us to confront the limits of our knowledge and to develop new theories that can describe the most extreme conditions in nature. So, what happens at the singularity? The answer depends on which approach to quantum gravity is correct, and we do not know yet. It might be a Planck star, a tiny core supported by quantum pressure. It might be a fuzzball of strings. It might be a bounce that creates a new universe. It might be something we have not even thought of yet. What we can say with confidence is that the singularity predicted by general relativity is not the end of the story. It is a signpost telling us that we need a better theory. And when we finally develop that theory, when we finally understand what happens at the Planck scale, we will have unlocked one of the deepest secrets of the universe. But we are not done yet. There is more to explore. Black holes come in different sizes, from tiny primordial black holes to supermassive monsters billions of times the mass of the Sun. Does the experience of falling in differ depending on the size? And what role do black holes play in the evolution of galaxies and the universe itself? Those are the questions we turn to next. We have journeyed into the heart of a black hole, confronted the singularity where physics breaks down, explored the quantum theories that might replace it, and surveyed the entire population of black holes from the smallest to the largest. Now, as we approach the end of our exploration, it is time to step back and consider the broader implications. What do black holes tell us about the nature of reality? What philosophical and scientific questions do they raise? And what mysteries remain unsolved? Let us begin with perhaps the most profound implication of black holes. They represent places where information appears to be destroyed, and this challenges one of the most fundamental principles in physics. We have discussed the information paradox at length, but it is worth revisiting because it cuts to the heart of how we understand the universe. In classical physics, if you know the state of a system perfectly at one moment, you can predict its state at any future moment and retrodict its state at any past moment. The laws of physics are deterministic and reversible. If you film a classical process and play it backward, you see something that is also allowed by the laws of physics. A ball thrown upward will come back down, and if you reverse the film, you see a ball thrown upward from the ground, which is perfectly reasonable. Quantum mechanics introduces uncertainty and probability, but it preserves a deeper form of reversibility. The evolution of a quantum system is described by a mathematical object called the wave function, and the wave function evolves according to the Schrödinger equation, which is completely deterministic and reversible. If you know the wave function at one time, you can calculate it at any other time, forward or backward. The probabilities change, but the information is preserved. This is encoded in what physicists call unitarity, the principle that the total probability is conserved and that information is never lost. When you measure a quantum system, the wave function appears to collapse, and you get a definite outcome. This seems irreversible, but most physicists believe that the measurement process itself is unitary when you include the measuring device and environment in your description. The information is not lost, just spread out and entangled with the surroundings in a way that makes it inaccessible. This is called decoherence. Black holes seem to violate this principle. When matter falls into a black hole, it crosses the event horizon and is lost to the outside universe. Eventually, the black hole evaporates through Hawking radiation, and the radiation is thermal, meaning it contains no information about what fell in. It is like burning a book and examining the smoke. The smoke tells you nothing about what was written in the book. If this is true, then information has been destroyed, and unitarity is violated. This would mean that quantum mechanics as we understand it is not a complete description of nature. It would mean that there are processes in the universe that are fundamentally irreversible, that erase the past. This is a radical idea, and most physicists are deeply uncomfortable with it. The alternative is that information is not destroyed, that it is somehow preserved and eventually released in the Hawking radiation, even though we do not yet understand how. This could mean that the Hawking radiation is not truly thermal, but contains subtle correlations that encode the information. It could mean that the information is stored at the event horizon and imprinted onto outgoing radiation. It could mean that the interior of the black hole is not separate from the exterior, but is dual to it, encoded on the horizon like a hologram. All of these ideas are being actively explored, and they have led to deep insights into the nature of space-time, quantum entanglement, and the structure of quantum field theory. The information paradox has become one of the central problems in theoretical physics, and its resolution will likely require a complete theory of quantum gravity. Let us consider another profound implication. Black holes suggest that space-time is not fundamental but emergent. In our everyday experience, space and time are the stage on which events unfold. We think of space-time as the background, the arena in which matter and energy interact. But black holes, and especially the holographic principle, suggest that this picture is wrong. The holographic principle states that all the information in a volume of space can be encoded on the boundary of that volume. This is deeply counterintuitive. It suggests that the three-dimensional world we experience is in some sense an illusion, a projection from a two-dimensional surface. It is as if reality is a hologram, and we are living inside it. This idea originally came from studying black hole entropy. In the 1970s, Jacob Bekenstein and Stephen Hawking showed that black holes have entropy, a measure of disorder or hidden information, and that this entropy is proportional to the area of the event horizon, not the volume. For ordinary matter, entropy is proportional to volume. A box twice as large can contain twice as much stuff and twice as much entropy. But black holes are different. Double the mass, and you double the area, not the volume. This suggests that the information about what is inside the black hole is somehow encoded on its surface. In the 1990s, physicists Gerard T. Hooft and Leonard Susskind proposed that this might be a general principle, that the information in any region of space is encoded on its boundary. This was a radical proposal, but it gained support from developments in string theory. In 1997, Juan Maldacena discovered a concrete example of holography in string theory, a correspondence between a theory of gravity in a certain type of spacetime and a quantum field theory living on the boundary of that spacetime. This is called the AD-S-CFT correspondence, and it has become one of the most important ideas in theoretical physics. It suggests that spacetime itself is not fundamental, but emerges from the entanglement structure of quantum fields on the boundary. In this picture, space is not something that exists independently. It is a way of organizing and describing the quantum information in the boundary theory. The geometry of spacetime, the curvature that we interpret as gravity, is a manifestation of how quantum information is distributed and entangled. This is a stunning reversal of how we usually think about things. Instead of quantum fields living in spacetime, spacetime emerges from quantum fields. Black holes are teaching us that the universe is, at its deepest level, made of information, and that space and time are derived concepts, useful for describing certain patterns in that information, but not fundamental. If this is true, then the question, what happens inside a black hole, might not even be well posed. The interior might not be a real place, but an emergent description that breaks down under extreme conditions. The singularity might not be a thing that exists, but a signal that we are asking the wrong question, using concepts that do not apply. This is speculative, of course, but it is grounded in serious theoretical work, and it represents a profound shift in how we think about reality. Let us turn to another mystery: cosmic censorship and naked singularities. The cosmic censorship hypothesis, proposed by Roger Penrose, states that singularities are always hidden inside event horizons. Nature, in other words, is modest and does not allow singularities to be visible from the outside universe. If cosmic censorship is true, then we can never observe a singularity directly. All the extreme physics, the quantum gravity effects, the breakdown of space-time, all of it is hidden behind an event horizon where we cannot see it. This is both frustrating and reassuring. Frustrating because it means we cannot test our theories of quantum gravity by observing singularities. Reassuring because naked singularities, if they existed, would be pathological. They would be places where the future is not determined by the past, where predictability breaks down completely. The laws of physics, as we understand them, would fail in the presence of a naked singularity. Is cosmic censorship always true? We do not know for certain. In classical general relativity, there are solutions that contain naked singularities, but these solutions are usually considered unphysical, requiring fine-tuned or unrealistic conditions. However, there are also scenarios where cosmic censorship might be violated. For instance, if you spin up a black hole by dropping matter into it in just the right way, you might be able to spin it fast enough that the event horizon disappears, leaving a naked singularity. This is called overspinning a black hole, creating what is known as a naked Kerr singularity. Whether this is actually possible is unclear. Some calculations suggest that the black hole would resist overspinning, that quantum effects or other mechanisms would prevent the event horizon from disappearing. Others suggest that overspinning might be possible under extreme conditions. Similarly, if you overcharge a black hole by adding too much electric charge, you could potentially destroy the event horizon and create a naked Reissner-Nordstrom singularity. Again, whether this is possible in practice is debated. The consensus among physicists is that cosmic censorship probably holds that nature has mechanisms to prevent naked singularities from forming. But we do not have a proof, and the question remains open. If naked singularities do exist, they would be extraordinary objects, windows into the Planck scale that we could observe from the outside. They would also be dangerous in a sense, as their presence would undermine the predictability of the universe. There is another profound question that black holes raise: the nature of time. Inside a black hole, the roles of space and time swap. The singularity is not a place but a moment in the future. This suggests that time is not as fundamental as we think, that it is tied up with the geometry of space-time in ways that can be radically different from our everyday experience. In our normal experience, time flows forward. We remember the past, but not the future. Entropy increases, and irreversible processes happen. This is the arrow of time, and it is one of the deepest mysteries in physics. Why does time have a direction? Why is the future different from the past? The answer is usually tied to entropy and the second law of thermodynamics, which states that entropy always increases. But why was entropy low in the past? That question leads back to the Big Bang and the initial conditions of the universe. Black holes complicate this picture. Inside a black hole, time flows toward the singularity. But what does that mean? Is the singularity the end of time, or is it a transition to something else? If loop quantum gravity is correct and there is a bounce, then time might continue on the other side, flowing into a new region of space-time. If that is true, then time is not a single line but a branching structure, with different branches corresponding to different black hole interiors. This is highly speculative, but it illustrates how black holes force us to reconsider even our most basic concepts like time and causality. Let us consider the observational future of black hole research. We have made enormous progress in the last few decades. We have imaged the shadows of black holes, detected gravitational waves from their mergers, and observed tidal disruption events and quasars powered by accretion. But there is much more to come. The Event Horizon Telescope, which produced the first images of black holes, is being upgraded. More telescopes are being added to the array, and new technologies are improving the sensitivity and resolution. In the coming years, we will get sharper images of black hole shadows, and we may be able to make movies showing how the accretion flow changes over time. We may also be able to test predictions of general relativity in the strong field regime near the event horizon, looking for deviations that could hint at new physics. The LISA space mission, scheduled to launch in the 2030s, will open a new window on the universe by detecting gravitational waves from supermassive black hole mergers. These events are too low frequency for ground-based detectors like LIGO, but will be clearly visible to LISA. LISA will also be able to detect waves from extreme mass ratio inspirals, events where a stellar mass black hole or other compact object spirals into a supermassive black hole. These events will provide exquisitely detailed maps of the spacetime around supermassive black holes, testing general relativity with unprecedented precision. There are also plans for next-generation ground-based gravitational wave detectors, like the Einstein Telescope in Europe and Cosmic Explorer in the United States. These will be far more sensitive than current detectors and will be able to see black hole mergers out to the edge of the observable universe. They will detect thousands or tens of thousands of mergers per year, providing a complete census of the black hole population across cosmic time. On the electromagnetic side, New X-ray missions like Athena and Lynx will study accretion onto black holes in unprecedented detail, measuring the spins of black holes, mapping the structure of accretion disks, and tracing how matter spirals inward. These observations will test our models of black hole accretion and help us understand how black holes grow and influence their environments. There is also the possibility, however remote, of detecting Hawking radiation. For stellar mass and larger black holes, Hawking radiation is far too weak to detect. But if small primordial black holes exist, and if one were to evaporate nearby, we might be able to see it. The final explosion of a primordial black hole would produce a burst of high-energy gamma rays that could be detected by space-based telescopes. No such bursts have been seen, but searches continue, and the detection of even one would be a monumental discovery, confirming Hawking's prediction and opening a window into quantum gravity. Let us also consider the philosophical implications. Black holes challenge our intuitions about reality in fundamental ways. They are places where cause and effect break down, where the future is not determined by the past, where information might be destroyed or radically transformed. They force us to confront the limits of knowledge. There are things about black holes that we can never know, regions of space-time that are forever hidden behind event horizons. This is not just a practical limitation, but a fundamental one, built into the structure of the universe. No matter how advanced our technology becomes, we can never send a probe into a black hole and get data back. We can never observe the singularity or the interior directly. The best we can do is theorize, calculate, and hope that our mathematics is a reliable guide. This raises a question. If something is in principle unobservable, does it exist? This is a version of the old philosophical question about the sound of a tree falling in a forest with no one around to hear it. In physics, we usually take a pragmatic approach. We say that something exists if it is part of a theory that makes testable predictions. The interior of a black hole is part of general relativity, and general relativity makes countless predictions that we have tested and confirmed. So, we have good reason to believe that the interior exists, even though we cannot observe it directly. But black holes push this pragmatism to its limits. If the singularity is replaced by quantum effects that we do not understand, then we cannot even write down the equations that describe it. We have theories like loop quantum gravity and string theory that make predictions, but we cannot test those predictions. We are in a regime where physics blends into philosophy, where we must make assumptions about what is real and what is merely mathematical. There is also the question of whether black holes are truly black. Hawking radiation suggests that they are not, that they glow faintly with thermal radiation. But thermal radiation carries very little information. It is the most generic, least interesting kind of radiation possible. If black holes only emit thermal radiation, then they are effectively black in terms of information. They give us no clues about what fell into them. But if information is preserved, if the Hawking radiation is not truly thermal but contains subtle correlations, then black holes are not completely black. They whisper secrets about their contents, encoded in the radiation in ways we do not yet understand. Decoding that information, if it is there, would be an extraordinary achievement, revealing the quantum structure of gravity and the nature of spacetime itself. Let consider one final mystery. Are there other kinds of horizons in the universe? Black holes are not the only objects with event horizons. In an expanding universe, there is also a cosmological horizon, a boundary beyond which we can never receive information. Due to the accelerating expansion of the universe driven by dark energy, distant galaxies are receding from us faster than the speed of light. There is a sphere around us, currently about 16 billion light-years in radius, beyond which light will never reach us. Anything beyond this sphere is, for all practical purposes, beyond the edge of our observable universe. This cosmological horizon is similar to a black hole event horizon in some ways. Just as you can fall into a black hole but never come back, a galaxy can cross the cosmological horizon and disappear from our view forever. Just as black holes have Hawking radiation, the cosmological horizon has a temperature called the Gibbons-Hawking temperature, though it is extraordinarily cold, far colder even than the Hawking temperature of a supermassive black hole. This raises a strange question. Are we living inside a black hole? Not literally, of course, but in terms of the causal structure. We are surrounded by a horizon beyond which we cannot receive information. We are in a region of space-time that is, in some sense, causally disconnected from the rest of the universe. This is one of the deep puzzles of cosmology, and it is connected to the question of how quantum gravity works on cosmological scales. There are also horizons in accelerating reference frames. If you accelerate constantly in flat space-time, you create a horizon behind you called a Rindler horizon. Anything beyond this horizon cannot catch up to you, no matter how fast it travels. The Rindler horizon has many properties similar to a black hole event horizon, including an associated temperature called Unruh temperature. An accelerating observer will detect a bath of thermal radiation, even in empty space, due to quantum effects near the horizon. These connections between different kinds of horizons suggest that there is something fundamental about horizons themselves, something that transcends the specific type of horizon. This is part of the holographic principle, the idea that horizons encode information about the regions they enclose. Understanding horizons, whether around black holes, in cosmology, or in accelerating frames, might be the key to understanding quantum gravity. So, where does all this leave us? We have traveled into the depths of a black hole, explored the singularity and the quantum theories that might replace it, surveyed the populations of black holes across the universe, and pondered the deep questions they raise about information, space-time, and the nature of reality. What can we say with certainty? Black holes exist. This is no longer in doubt. We have observed them through their gravitational effects on nearby matter, through the gravitational waves from their mergers, and through direct images of their shadows. They are real, physical objects, not just mathematical curiosities. Black holes are described, to excellent approximation, by general relativity. The predictions of Einstein's theory have been confirmed in every test we have conducted. The shapes of event horizons, the dynamics of orbits around black holes, the gravitational waves from mergers, all match the predictions of general relativity with stunning precision. Black holes have profound effects on their surroundings. They power quasars and active galactic nuclei. They regulate star formation in galaxies. They tear apart stars that wander too close, and they anchor the structure of galaxies through their gravitational influence. What do we not know? We do not know what happens at the singularity. General relativity predicts infinite curvature and density, but this is almost certainly not the full story. Quantum effects must become important at the Planck scale, but we do not have a complete theory of quantum gravity to describe what replaces the singularity. We do not know how information is preserved in black holes. The information paradox remains unsolved, despite decades of work. We have promising ideas, like holography and black hole complementarity, but we do not have a complete, accepted resolution. We do not know if firewalls exist at event horizons. This is tied to the information paradox. If information is preserved, does that require a violent firewall at the horizon, or can the horizon remain smooth as general relativity predicts? The question remains open. We do not know how supermassive black holes formed so early in the universe. The mechanism by which black holes of billions of solar masses appeared less than a billion years after the Big Bang is still unclear. We have ideas, like direct collapse or super Eddington accretion, but we do not have a definitive answer. We do not know if cosmic censorship always holds. Can naked singularities form, or does nature always hide singularities behind event horizons? This is a fundamental question about the structure of spacetime. We do not know if primordial black holes exist. If they do, they could account for some or all of dark matter, but searches have not found convincing evidence for them. These unknowns are not failures of science. They are the frontier, the edge of our knowledge, the place where the next generation of physicists will make their mark. Black holes have taught us more about the universe than perhaps any other single phenomenon. They have forced us to confront the limits of our theories, to develop new mathematical tools, and to question our most basic assumptions about space, time, and reality. They have revealed connections between gravity, thermodynamics, quantum mechanics, and information theory that no one suspected before. They have opened new ways of observing the universe through gravitational waves and images of event horizons, and they have inspired countless people to wonder about the cosmos and our place in it. In the end, black holes are reminders of how much we have learned and how much remains to be discovered. They are monuments to the power of human curiosity and ingenuity, testaments to our ability to understand even the most extreme and alien environments through mathematics and observation. They are also humbling, showing us that the universe is stranger and more wonderful than we can easily imagine. The journey into a black hole is a journey to the edge of knowledge itself, to places where our best theories break down and new physics must take over. It is a journey we can only take in our imaginations, guided by mathematics and observations from afar. But it is a journey worth taking, because in trying to understand what happens inside a black hole, we are trying to understand the deepest secrets of the universe. What is space? What is time? What is information? How does quantum mechanics fit with gravity? These are questions that black holes force us to confront, and answering them will reshape our understanding of reality. So, what happens inside a black hole? The honest answer is that we do not fully know. We have pieces of the puzzle, tantalizing clues from general relativity, quantum mechanics, and string theory. We know that you would cross the event horizon, fall toward a singularity, and be torn apart by tidal forces. We know that the singularity predicted by classical physics is probably not the end of the story, that quantum gravity intervenes to create something else, a Planck star, a fuzzball, a bounce, or some structure we have not yet imagined. We know that black holes are not just cosmic dead ends, but laboratories for testing the most fundamental laws of physics. And we know that the quest to understand them is far from over. Every answer raises new questions, and every observation opens new mysteries. Black holes are not just objects in the sky. They are windows into the ultimate nature of reality, and as long as they continue to defy our complete understanding, they will continue to captivate and challenge us. That is what happens inside a black hole. Not a simple answer, but a profound mystery that will occupy scientists for generations to come.